Okay, office hours, here we go. Let's do a couple from quiz 3 first, and then we'll go to 4.2, and then we'll get some of these concept ideas that are this week ideas. But quiz 3, since the questions from quiz 3 are really looking at historical things, let's go ahead and start with quiz 3, number 1. Does somebody have that up?
Yeah, it's, for me, it was 1 atom of tin weighs 1.971 times 10 to the negative 13 nanograms. How many tin atoms are in 1.272 grams of tin? And then how many moles of tin are there?
1.2, wait, how many grams was that?
1.272 grams of tin. And then how many moles of tin are there?
Okay, so this is unit analysis from a while back, week 1. Okay, so how do we do this? This is nanograms, and this is, I'm going to put nanograms per an atom, right? That unit is kind of implied because it told us 1 atom of tin is equal to that, so it's nanograms per an atom. I want to know how many atoms?
Yeah, how many tin atoms?
How many atoms? So when I look at this, there's some pretty straightforward unit analysis to do, right? I'm going to switch colors to be dramatic, but I've got my 1.971 times 10 to the minus 13 nanograms per 1 atom, and I've got my 1.272 grams. First thing I'll notice is that my units don't match, so I have to convert my units. I either have to make this one into grams or this one into nanograms. Either way works. Normally I would just make this one, I can just make this one grams, and that's going to be a 10 to the minus 9, so that's going to switch that to a minus 22. Let me do that separately just to make sense of it, but once you get good at unit analysis, you can do that sort of thing. So what we have is 1.971 times 10 to the minus 13 nanograms per an atom, right? And then I'm going to multiply by 1 gram is 1 times 10 to the 9 nanograms. I'm going to go ahead and flip that because I don't like division as much. I'm going to say 1 times 10 to the minus 9 grams per 1 nanogram. Right? A nanogram is really tiny, so a small fraction of a gram is a nanogram. When I multiply these two together, it's going to be minus 13 plus minus 9. That gives me minus 22. And once we practice this enough, we just kind of, I see the nano, I'm like, oh, 13 is going to be 9 lower. So it's minus 13 minus 9 is minus 22. Now that I've got my units, so that was the first thing, was that unit analysis. But now it wants how many atoms. So I've got to have some mathematical operations where I end up with the unit of atoms on top. Now, the units in problems are huge hints. One of the things that I saw in the midterm that was a really big problem was people writing down numbers without units. This isn't a math class. It's not just numbers. The units are trying to point us in a proper direction, and they're trying to represent something in the physical world. The representing the physical world is the thing that's important to me because chemistry is all about the real world and making the real world like measurable. But for you all, it's probably how the units give us hints to our process that's going to be more valuable. I want to end up with atoms on top. There's no atoms in this one. Atoms is on bottom with this one. So what do I have to do? I'm going to have this inverted. So I'm going to have 1.272 grams times 1 atom for 1.971 times 10 to the minus 22 grams. So in order to get atoms on top, because I knew my answer was in atoms, I knew this thing had to be flipped over. Once I have that thing flipped over, I'm like, oh, I also want to get rid of the grams. So if I just multiply the grams on top, the grams on bottom will cancel. Grams cancels grams. I'm going to be just left with atoms. The other thing we can think of, before we plug this into our calculator, do we expect a lot of atoms or a few atoms? A lot. How many atoms do we usually see on the human scale? like an Avogadro's number of atoms. Like something that's like 6 times 10 to the 23rd. So we expect our numbers to be pretty big. So now that I'm expecting something to be pretty big, I'll plug this into my calculator and see how big it is. 1.272 divided by 1.971 times 10 to the minus 22. 6.4 times 10 to the 21 atoms. Right? Huge number of them. 6.45 times 10 to the positive 21 atoms. And again, at this point in the quarter, I really often start putting the explicit positive 21 there, just so I know that I didn't accidentally forget a negative or include a positive or something like that. I just have to do that for myself, because if not, I instinctively do so much stuff in chemistry as a negative exponent that I just automatically start throwing negatives if I'm not careful. So I put the positive explicit where I'm like, no, it's positive, it's supposed to be positive, don't put a negative sign, that's on purpose. So that's how we get part 1 of the question. And then part 2 is just, do we know how to convert atoms to moles? So, definition of a mole. Right, we got our 6.022 times 10 to the 23rd things per mole. And again, we can do this logic of how the units helps us. I know I want an answer that is equal to moles. I wrote atoms twice, that's funny. I got this number of atoms. I got this number of things per mole. What am I going to have to divide by if I want to get moles on top? I'm going to have to divide by this thing, right? This has moles on bottom. I want moles on top. So that means I have to divide by this to get moles on top. So when I do my math, I'm going to have my 6.45 times 10 to the 21 atoms times 1 mole divided by 6.022 times 10 to the 23rd atoms. And I just write atoms because in the context of the problem, my things is a number of 10 atoms. But notice, flipping this thing over, so I'm essentially dividing by this, I've got it flipped over. I've got moles on top, so my answer is in moles. I take that number, I divide by 6.022 times 10 to the 23rd. 6.45 times 10 to the 21 divided by 6.022 times 10 to the 23rd. And I am getting 1.07 times 10 to the minus 2 moles. Unit analysis is the core of this problem. This is something we did back in week 1. Comes back. It was a pretty missed question in week 1. It was also missed on the online version of the midterm, so I thought I'd give you all another chance to be reflective, go back and look at it, figure out what went right, what went wrong, give it to you another time. I think it went better. Now I'm curious what the percent right on quiz 3 was for this problem. Oh, and I also have to put this down a little bit. Oh no, that's not everything. Okay. So just out of curiosity, bear with me a moment. Quiz 3. Jeez. Okay, well that's better, but it's not great still. Percent correct on that problem was 58%. Which is not as high as I'd like it to be, given that it's like the 3rd time we've seen it. In any case, unit analysis, making sure we've got our nano correctly, but it's just mass divided by mass was all it really was. And then atoms divided by Avogadro's, and it's just like the whole problem is 2 divisions. Like I could have done it much faster. I could have been like honestly, I could have been this divided by that divided by that, and then whatever we got divided by Avogadro. Like it's quick mathematically. I walked through it a little bit slower because I know that process of being reflective, being able to look at a problem and be like, where are the hints in the problem? What's the core of it, right? So if I wanted to write down, is it okay if I erase this? Okay. If I wanted to write this down, if I was if I was doing, let's say I'm at home, I'm making an answer key for this. Here's what mine would look like. 1.272 times 10 to the 9 divided by 1.97 times 10 to the minus 13. That's all I have to write down. I converted this one into nanograms, so I didn't have to mess with the minus 22 thing, but the answer is going to come out the same. Then my next one would be take all of that divided by 6.022 times 10 to the 23rd. That's going to be my next answer. And that's it. That's the entire problem. Now, doing math like this completely strips out the context, the understanding, the ideas, but like that's literally the entire problem in terms of what we have to punch into our calculator. So, the context matters. How we use those hints inside of the problem matters. How we use the units to kind of give us an idea of what we're getting to. All of that's important. Not just, and like I try to really stress these things in terms of they're not those types of skills are not just important for a chemistry class. Those types of skills are important for the rest of your college career and probably whatever career after college you get into. Those types of like, I can look at a problem and I can think about how to solve the problem and what I know about a problem and what I need to do with the problem. That's the core skill you're learning in college. That's the thing that you're learning here that people are willing to pay you thousands of dollars a month to do. So that's what we've got to focus on. That was number 1. Let's go ahead. We ready to go on to number 4, the number of photons? Sorry, I forgot to say the last one was from quiz 3. Number 4.
How many photons are emitted in 3 seconds from a 55.5 watt UV lamp?
Oh, hang on a second. A 55.5
watt UV lamp that produces 87 nanometers of light.
Okay. And I think it also tells you a watt is equal to 1 joule
over 1 second
per second. Okay. Because that's a physics thing. I don't expect you to memorize that. Okay. We need 2 important equations to do this problem. How many photons? So we've got something that's in terms of some energy per second. We've got a number of seconds. We've got a wavelength. What's the important equation here that's not told to us that we need?
The energy of a photon.
Right. Energy of a photon equals hc over lambda. We can go ahead with our 87 nanometers. We can go ahead and calculate 6.626 times 10 to the minus 34 joules seconds. 2.99 times 10 to the 8 meters per second. Divided by, do you all know my trick for converting nanometers? I write the 87, the nano just becomes times 10 to the minus 9 meters. I could have made it 8.7 times 10 to the minus 8 meters, but that's a quick way to do the nano conversion. So I can find this energy of a photon, and then we'll talk about the equation that I didn't give to all of you because I thought it was reasonable, but we'll talk about that in a minute. Times 2.99 times 10 to the 8th divided by 87 times 10 to the negative 9, and we get 2.277 joules. Now, it doesn't say this in the units, but this is joules per 1 photon. Right? This is the energy of a single photon, so this is the oh wait, whoa. Sorry. I forgot something really important. Times 10 to the minus 18 joules. Right. That minus 18, remember, minus 18, minus 19, minus 20, that's our typical energy of photons if they're around the visible spectrum. So this is a reasonable energy for a single photon. What if I had 2 of these photons? How much energy would I have? Double it, right? It'd be like 4.4. What if I had 10 of these photons?
22.
Times 10. What if I had 576 of these photons? Times 576, right? So in our heads, we kind of understand this idea that the total energy is going to be the number of photons times the energy of the photon. And this is the equation I didn't give to you because I thought it was self-apparent of like, if you have 5 photons, you have 5 times the energy. If you have 500 photons, you have 500 times the energy. If I give you two $20 bills, you have $40. If I said, how many 20s does it take to have $758 billion? 758 billion divided by 20 gives you the number of bills, right? This is just kind of something that we understand from working with numbers and quantities of things. But when I put it in the context of photons, people are like, nope, 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 it's photons. This doesn't make sense. It's fair to kind of feel that way because this is definitely a different context, right? And this is one of the things that makes chemistry so difficult, is you've been living in this world, I don't know how old you all are, but like, 18 to 20, something like that, right? So you've all been living in this world for the last 18-ish years, and you've probably never thought about the chemical structure of the rubber in your boots. About how it's like cross-polymerized chemical compounds made of hydrocarbons that are like petroleum-based, right? You've probably never, like, you're all writing with pencils, you've never probably thought about the intermolecular forces of graphite on cellulose. You've probably never thought about the porous nature of cellulose, the cellulose being what makes paper, right? There's all these details in the world where you've been existing and living for the last 20 years that you've never thought about. And chemistry is asking you to think about all of those things. Take this world that you've been going through for the last, number of years and think about it in a completely different way that's been around you this entire time that you've never noticed. It's weird. It's difficult. And it can be really challenging. But once you grab on, for me, hopefully for you too, once you start to grab onto that thread of like, oh, I can think about the world this way, like, it's just, everything is different. Like, you just, like, the way you look at the world is different. The way you think about the world is different. And it's really, for me, it's really exciting and it's really interesting. That's part of why I love teaching chemistry, is like, people, when they start being like, oh, I can read the ingredients on the back of my ice cream and I can actually pronounce all of them, and I can understand, like, I can look at them and be like, oh, I know what functional groups are in there. I know that this is like this type of hydrocarbon. I know that, like, I could look up the structures and I can make sense of them. Like, it's kind of a weird thing that, like, you've never thought about the chemical compounds in your food, even though they're all listed on the back, and you've probably looked at them and been like, I don't know what those are. Like, shampoos, they talk about, like, sulfates in your shampoos. We're going to learn about what those are too. Right? There's all these ways we interact with it, and now it's like, oh, we're interacting with it in a way where we're starting to understand this world that we're interacting with, and we're understanding on a different scale. And that's where this idea of, like, the total amount is the number of the small unit times how many of them you have. Like, it's really odd. Like, it totally makes sense. But I put it in the context of photons or the context of molecules or atoms, and it's like, that's really weird. It's because it's on a scale. It's a way that we've never thought about it, even though the idea is the same. So, okay. Do we expect? So here I want 55.5 joules per second. How many seconds? For 3 seconds. That's going to get me my total energy. That's going to be like 166.5. Wow, I can't believe I did that correct in my head. 166.5 joules. That's my total energy. My number of photons that I'm going to have is going to be, to get that total amount of energy, I need a certain number of these photons. So I'm going to have 2.277 times 10 to the minus 18 joules. Units of joules will be canceled out. I'll be left with a number of photons. Again, it's implied that this is joules per photon because that is the energy of a single photon. Do I expect it to be a lot of photons or a small number of photons? A lot. Like a lot. Each photon only carries a fraction of a fraction of a fraction of a joule. So if I want to get a lot of joules, I'm expecting it to be a big number. So I'm going to go ahead and I'm going to divide that over. I'm going to divide by 2.277 times 10 to the minus 18. And I'm going to get 7.31 times 10 to the 19 joules. Sorry, not joules. Photons. Joules cancels out as a unit, and I end up with a certain amount of photons left over. And it's a huge number of photons, right? I need a lot of photons to add up to that amount of energy. This number of photons is more stars than in our galaxy. It's a lot of photons, right? I have no way of making sense of the size of this number. It's like that number is bigger than the number of grains of sand in California. Like it's a phenomenally giant number. I can't make sense of it. I can write it down, I can point at it and be like, wow, that's a big number. But like to put it into context that makes sense on a human scale, no way to do it. Okay. Now, again, in terms of like the math we did a multiplication, a division, and then another division. That was like all we had to do mathematically. But using the different clues, you got to go to another class?
Yeah.
Okay. Did you get all your questions answered? Okay. Talk to me more if you need to talk more. More questions will be on YouTube if you wanted some of these other questions answered as well. Okay.
Thank you.
See ya. So, again, mathematically, there are only a couple steps, but the point isn't, we're not in a math class, right? It's how does that math relate to the physical world? How does that physical world relate to something that's useful and interesting in the context of chemistry? For a lot of you, you're like, I don't care about that interesting stuff. Well, interesting to me, you're like, how do I get the points? I know, that's the thing with like, getting into that interesting stuff is how you get the points, because then like all of it starts to click, all of it starts to reinforce itself. Questions on this, or are we ready to move on? Okay, let's go ahead, let's pop over to 4.2, which I just released the feedback for that, so you can see which questions on the graded questions, you can see which ones you got right and which ones you got wrong. I also released the feedback for quiz 3 just before office hours today, so you can look at that as well. But let's go ahead, let's look at 4.2, and we're looking at number 5 and number 8, and then we'll look at some general concept questions.
Number 5 was draw a line angle structure for C5H8.
Just one?
Yeah. I think I eventually got it, I just said do not understand, so I figured I'd ask. Oh my gosh, okay. There we go.
What'd you put?
I'm not quite sure. It was like I don't know.
So there's, let me show you a quick trick. How many of you are going to take OChem, organic chemistry? Okay, let me show you a quick trick that I find really useful for figuring out when I need double bonds and when I don't need double bonds. So when I look at my C5, 2, 3, 4, 5. Wait, is this even right? Oh no, I need another double bond in that for it to be right, sorry. So when I look at this, if I had a saturated chain, 2, 4, 6, 8, 10, 12 hydrogens. So saturated, so a saturated chain would be number of carbons times 2 plus 2. So saturated, if this was, for example, C5H12 would be saturated. That would be no double bonds. It would just be a straight 5 carbons in a line, no double bonds. 2 less, C5H10, 1 degree of unsaturation, you need a double bond. 2 less, C5H8, 2 degrees of saturation, I need a double bond, or I need 2 double bonds, or a triple bond, or a ring and a double bond, but I need to do something so I have less hydrogens in the structure. So Not something I'm going to stress this quarter, but since most of you are taking organic chemistry, looking for that degrees of unsaturation becomes a really nice clue for like, how many double bonds do I need? How many triple bonds? How many rings do I need? Like how do I need to change the structure? So as soon as I saw that it was C5H8, I did my math wrong. That's why I forgot the +2. That's why I only did one double bond. But as soon as I saw that it was C5H8, I was like, I know I need at least one double bond or a ring. There's a lot of different isomers we could draw for this, but that degrees of saturation is one thing to think about. So now if I do my count, that's 1, 2, 3, 4, 5, 6, 7, 8 hydrogens would be needed to fill it out. So 2 degrees, so I'm going to have C5H8 like that. Another thing you could do, a ring with a double bond. The ring, since I've got a carbon hitting a carbon, that takes care of 2 hydrogens. The double bond takes care of 2 hydrogens. I could also do a chain with a triple bond. That takes care of, that one's going to have no hydrogens. That's also going to be a C5H8. I could also do some branching with different bonds, different places, right? I can do, if I add branching in, there's a whole bunch of other structures I can make with branching as well. Got my 1, 2, 3, 4 with my 1 off to the side. And the double bonds could be double in there, could be double in there, could be double, there's a lot of different places. Actually, this has a bunch of resonance structures to it as well, which we should talk about. We're only doing like the very introductory idea of resonance structures. We talk more about it in Chem 129. And then it becomes a really important idea when you get to organic chemistry. But we're just kind of introducing the idea, so when you get to Chem 129, it's not the first time you've seen it. So I'm not going to do the resonance structures with these things. But since this has I'm not even going to say the words. We'll deal with that in 129. So there's a lot of different structures that we can draw for C5H8. Doing it slowly and counting is one thing. Remembering that we can add double bonds and triple bonds is a thing. Remembering we can add rings is a thing. And then remembering we can do branching gives us a lot of opportunities to make a lot of different Lewis structures with C5H8.
Okay. And then number 8, I just looked at it again and I see what I did wrong.
What was number 8? I'm still
It
curious.
was just deciding whether 2 structures were isomers or not.
Were they isomers or were they the same thing?
They were not, no.
Okay, cool. Okay, in that case, let's talk about resonance structures and the CO3 2-. You bet, see ya.
Thank you.
So, resonance structures and CO3 2-. Let's draw the Lewis structure for CO3 2- first, and then we can look at what's up with resonance structures and CO3 2-. I've done this a couple times, so I can just kind of do it like this. Here's my 2-. My formal charges work out where I've got a minus formal charge on that oxygen. I've got a minus formal charge on that oxygen. I want to make sure I've got my full valence shell for each thing. So this has 8 electrons around it, this has 8 electrons around it, this has 8 electrons around it. Got my full valence shell. My things that are more electronegative tend to be the things that have the negative formal charge, have more electrons around them. And this is the Lewis structure for CO3 2-. The systematic way to go about it, which is in the lecture slides, is we count our valence electrons, we make a skeletal structure, we fill our valence shells, and then we check it. And if it's bad, we repeat.
How do you know like where to put the minuses?
That was from doing a formal charge calculation. I just already knew it because it turns out oxygen with 1 bond is a formal charge of -1.
Okay.
And I just know that one from doing it a lot.
Okay.
Now, follow-up question. Is the double bond here? Or is it here? Or is it here?
Isn't it where it is? Because like that one has like less lone pairs.
Couldn't the electrons move around though?
I guess so.
That's resonance structures. So the whole idea of resonance structures is where you've got multiple Lewis structures with the same minimum formal charge. Right? So when I look at this one, right? I could have also drawn it like this. Right, and so essentially what's happened is these electrons have hopped over here, these electrons hop. These two go here, these two go here. Right, and so when you get to organic chemistry, you have this whole thing called like the arrow pushing model where you kind of push your electrons around, right? My electrons kind of jump around. Now, why does that happen? Well, this oxygen and this oxygen are equally electronegative, right? They have the same pulling force on those electrons. So if this oxygen pulls those electrons away, this oxygen, the carbon might pull the electrons over a little bit. And there's this push-pull happening between the different elements. And in fact, I could also do this one, where I've got it going to the bottom. Same idea, the electrons are getting pushed and pulled all over. Now here's the catch, and this is the part where it kind of gets weird, where we need resonance structures. Which of these three is the right structure? The answer is none of them, because it's all of them together at the same time. Right? It's like, okay, let me do my favorite thing. Okay, I'm going to draw a stick figure. Let's see if I can do it right. Nope, that looks terrible. Right? What's that stick figure doing?
Running?
Yeah. How can you tell the stick figure's running?
Shape.
Right? Is there anything like, what if the stick figure is just standing there like this? Like, right? There's some interpretation that needs to be put into our simple pictures. I'm amazed that you could tell the stick figure was running from that picture, right? But stick figures is like, and it's a person, right? That stick figure is a person. It's not an alien. It's not a dog. It's not a cat. It's a person running, right? There's this interpretation we have from childhood of how we draw and how stick figures, like the shapes of stick figures and what it's communicating. Lewis structures are the cartoon stick figure version of molecules in a chemistry class, right? That is in no way what the CO3 2- actually looks like, but it's our stick figure representation of it. And it's just a snapshot of something that's running. So with that running stick figure, can you imagine what the next step would be? What it would do next? And like you can imagine like the arms all kind of like move, arms and legs moving, right? We have to do the same thing with the electrons kind of dancing around the molecule. And that idea of the electrons dancing around the molecule, that's resonance structures. So you don't do this, probably about middle school. You start making the, like, you get bored in class, you make the little flip book pictures on the sides where it's a bunch of stick figures, but now it actually looks like it's running. That's what we need to do with the resonance structure. So if I wanted to make a really nice resonance structure drawing, I would draw these three things like 800 times on a flip book, and I would just constantly flip it for you, and it would look like things are just kind of dancing around and moving, and I'm like, okay, so what's the real structure? And it's like, well, it's everything dancing around and moving, and it's like, if I ever want to talk about it, I don't talk about like this point or that point or that point. I talk about the average of these three things together, because anytime we stop flipping through and we point at one, it has an equal probability of being one of those things. And so generally, it's the average of those three things. And always, when I make analogies like this, the stick figure analogy, the flip book analogy is not perfect, right? The rate at which these things are moving is so fast that it's not actually looking like it's flipping from like two single bonds and a double bond. It's always just the average of the three things. I can't draw that very well, so I go with my Lewis structure, and I leave it to everyone else who's looking at my Lewis structure to interpret the motion, the dynamic behavior of it. Just like you look at the stick figure and you're like, oh, the stick figure's running. Or dancing maybe, I don't know. But it's moving, right? It's doing something. And the interpretation is from our experience with that. Same thing happens with resonance structures.
So what it's saying is that basically like these three are the available resonance structures for CO3 -2.
Yes.
And like, but you can't it's so fast that it would never like be like this. It's just like the average of them.
Exactly.
But no matter which one it is, it's always gonna be, the double bond is always gonna be with the oxygen that has 2 lone pairs.
Yeah. Yeah.
But it doesn't matter. But it can be in any of those locations.
For now, yes.
Okay.
Right. It actually goes a step further than
Oh.
that, and this is the problem with Lewis structures, right? So if I wanted to draw this picture, and this is where we get to electrostatic potential maps, which I showed you a picture of one of those, but it's like what we should really draw, right? What we should really draw if we wanted to understand this is like I've got electrons that are kind of like moving across this cloud. And they're spread out. So we talk about the real definition of like resonance structures is localized versus delocalized electrons. So the fact that the double bond could be anywhere means that the double bond is kind of like everywhere at once. It's what we call delocalized.
Okay.
Whereas the single bonds, they're all kind of stuck in the same spots. The single bonds aren't changing. Those are localized. And I just like that picture with the green scribbles on it, that's probably the more accurate way to draw it, but makes a lot less sense.
Yeah.
Right? And that's where like computer simulations get really nice. You can look at the fancy term is electrostatic potential map. So that's a map of like they do a color grading on it of like where are the electrons more often, where are the electrons less often, and you get this nice kind of like picture across the molecule. We're actually going to be looking at some of those when we talk about intermolecular forces today in class. So we're going to talk more about electrostatic potential maps for this idea of it's not a single bond and a double bond, it's like a bunch of single bonds with an electron cloud delocalized across the molecule. That's part of why when I do my -2, like the green minuses, those are formal charge, the -2 is just spread across the entire molecule. That -2 is delocalized across the structure. It's not like the -2 is on this side and not on that side. It's spread across the entire molecule. And it's a weird idea, right? That's where I stopped and was like close enough for now.
Yeah.
It's because like we need to get that first idea, and then we can be like, wait, what does it really mean for it to be flipping between all of these? And is it really flipping, or like why does Dr. Erker keep saying it's not really flipping, it's the average?
Yeah.
And what does it mean if I took the average of these 3 things? And that's the next step. So right now, if it's just like, oh, it's this flipping thing, that's a good starting spot.
Okay.
But we eventually have to advance to that idea of the averaging.
Okay. And then you say the -2 is just everywhere. What is the -2 made of? Like,
2 extra electrons.
okay.
2 extra electrons
Are just
delocalized across the molecule.
Okay, so they can kind of, and that's why we're getting these 3 different.
Yeah, because
Okay.
they're kind of bouncing around all over the place. And this is one of the big problems with drawing Lewis structures is I spent several weeks being like, electrons are dynamic. They have like S, P, and D shapes to them. They have probability distributions. And then I'm like, never mind, they're just dots, right? And I warned you when we were first doing Lewis structures that like Lewis structures is like the cartoon picture, and then we have to add like getting to resonance structures and like if a line angle drawing is a stick figure, an electrostatic potential map would be like a 3D animated cartoon versus stick figures. Some people, my nephews love the 8-bit video games. They like the pixelated games. I'm just like, why? In any case, but like so there's like different levels. Like when you start using computers to look at molecules, you get a lot better idea of what the 3-dimensional shape and structure and distribution of electrons looks like. And we're going to be using for the Intermolecular Forces Lab, which we might start today, might wait till Thursday. We're going to be looking at some computer simulations and looking at some like 3D maps of where the electrons really are to move away from the stick figures to the more realistic pictures.
So on, I think it was 4.2, on number 8, there was one where it's like just carbons and hydrogens, but it's like, oh, are these 2 isomers? But they're not because they're resonance structures. Like, how do
let me
you
see.
tell the difference? Because I think I
Oh,
like
these
asked
aren't
somebody.
resonance structures.
Okay, because I had asked
Let me-
somebody and they were like, oh, it's not that, it's a resonance structure.
It's not a resonance structure.
Okay.
But let me show you what's going on with that one. I actually answered this for somebody else. So this one, and this is where flat world gets troublesome, right? So here, wait, this is too many now. Can I see the problem again?
Yeah.
I added some extra things on here that were not necessary.
It's like C9, I think, H.
Okay, so let me see here. We got a 1, 2. 1, 2, 3, 4. So there's my 4 chain. And oh, I remember what it is. 1, 2, 3, 4, 5. Okay. Yep. And then second carbon over. And second carbon over. Okay. So here it is, right? And that kind of looks like the first structure, right? So if you're looking at, this is back to 4.2 number 8. Here's the structure. And the difficulty with looking at these as flat static pictures is we forget that they're three-dimensional objects that not only can we rotate it in space, but the bonds, as long as they're single bonds, the bonds can also rotate in space. And so I can rearrange it so it looks like this, and now it looks pretty different. But the definition of an isomer is the same molecular formula with a different Lewis structure. To have a different Lewis structure, I need to break bonds and make bonds. So if I just do some rotations and end up with something that's like, looks really different, this would probably have too much steric hindrance to actually happen. Let me flip that up. Okay, that feels better. Right, looks really different, but it's still the same molecule. So it's not that it's an isomer, it's not that it's a resonance structure, it's the exact same molecule, just drawn a little bit differently to try and represent the different three-dimensional orientations that are possible.
Oh, that makes more sense, because I had asked somebody about it and they're like, oh, it's a resonance structure, but then I was like looking up and like the resonance structures and I was like,
Not a resonance structure, it's the exact same structure.
Okay.
Right? This was also, I feel a little bad about this. Not terrible, but a little bad. The reason I don't feel bad is because the word another was in bold and underlined on the problem on the midterm. But there was that problem where it was like, iron has several stable isotopes. The most common is this, pick another isotope. About a third of the class picked the same isotope. They picked, I think it was like iron 56 or something like that. About a third of the class picked the protons and neutrons for iron 56. They didn't pick a different isotope of it. Same thing, you just picked the exact same thing twice. It's like number 3 or 4.
Wait, I had a question about this. So like our next midterm is like cumulative, right?
Ish. Before we start
okay,
talking about
sorry,
midterm,
sorry. any
any other questions about content stuff? Okay, I'll talk a little bit about the midterms then. Next midterm, so the final exam is definitely completely cumulative. The next midterm, the reason I say cumulative-ish is the same way that the quizzes are kind of cumulative-ish, right? Like the quizzes focus on the newest material. The newest material is always the thing that I try to put more of. Quiz 3 was a little bit weird because we didn't have a lot of new material because we had a midterm that past week. But there's always the possibility of other things coming back. For exam 2, that will probably pick up at, what was the last thing? It'll probably pick up around periodic trends.
Yeah.
Right, because periodic trends was kind of saddling a little bit on the last exam, a little like end of the last exam, beginning of the next exam. So it'll focus on like periodic trends on. But to do periodic trends, we need to do electron configurations. To do electron configurations, we need to know atomic structure. So there's always some things that are kind of like interdependent, like especially in a chemistry class. I can't say it's only on new material because the new material depends on the old material.
Yeah.
So it's going to focus on the new material, but because the new material depends on the old material, there'll probably be a little bit of old material there too. Now, that does mean there probably won't be a Rydberg equation problem on there because none of the new material depends on Rydberg equation. I'm thinking if that's completely true. I think that's mostly true.
Okay.
Right?
Yeah.
Depends on how creative I want to get with the problems. But, you know, there's not really anything in the new material that depends on Rydberg equations.
Mhm.
As we start to look at bond polarity and intermolecular forces, we're definitely going to have periodic trends in electron configurations and electronegativity, and all that stuff is going to matter. So some of that's like all of that stuff, which was some of that was fair game, like the electron configurations and atomic structure was fair game on the first midterm, will also be fair game on the second midterm.
Got it.
Would you say that you like see students do better on the second midterm?
Depends on the class. And what I mean is when I'm teaching 124, which is the chemistry for like physical sciences and engineering, they tend to do better on the first exam and worse on the second exam because they do really good identifying equations and manipulating equations. In my 127 class, it's flipped where they usually have a harder time on the first exam and do better on the second exam. Because the first exam, like the whole math thing is just like, don't like it. And like all of the concepts and ideas and definitions, because like the second exam is like, how many times have we had to touch our calculator in the last week and a half of class? Right? Yeah, so like this week in class, we're still not going to be touching our calculators. So lots more key terms, concepts, and stuff like that. So my 127 classes tend to do a little bit better on the second midterm, like do better on the second midterm than the first.
Okay.
That's why I say it depends on the class.
Yeah.
With this, not with you all, but with this class and the distribution I have for the first midterm, dear Lord, I hope you do better on the second midterm. You can't, like, that midterm average is the lowest I've had in 8 years. There's lots of different variables for why that might have happened. It's definitely, like I showed you all the grade distribution, it's more students below 40% than I've ever had, which boggles my mind. I'm at a loss to figure out exactly what to do about that. I send emails out to students who fail the first exam, and usually I send out like 5 or 10 emails. I had to send out like 26 emails. Like, it's a lot. And it's strange because without that giant spike at 30%, the average would be almost 70. Instead, it's 52. It's wild to me. In any case, that's so point is, I really hope the average is better on the second one. I'm hoping that exam was a real big wake-up call for a lot of people where they're gonna like really, change, not necessarily double their effort, because a lot of people put in a lot of effort and don't do well, and it's not the fact that they're putting in effort, it's how they're putting in effort that they need to change. So I'm hoping that there's that kind of wake-up call of like, I need to change what I'm doing. I can keep studying the same amount. Maybe I need to study more. Like if I'm being, like I know some, like one of my students was like, oh, I study for this class a lot, like almost 2 hours a week. And I was like, that's your idea of a lot? Okay. I mean, we're in class for 6 hours a week. The simple mathematics is you should be studying like 8 to 10 hours a week for this class if you're doing 6 hours in class. They used to say 12, but I think it's too much. Yeah, there's other things to be aware of. How many units are you all taking?
I'm taking 12.
12?
I'm only 14.
14?
17.
Oh my goodness. You're the one I need to talk to.
15.
15. Okay, 12 is considered full-time.
Yeah, they
So-
just like blocked me into that.
So, but here's the math you have to do. So 12 hours is like a 40-hour work week, right? How many hours? So it's like 17. How many hours are you in class?
Like today, I'm in class for 5
In a
hours.
week.
Oh, in a week, I'm in class, oh my gosh. 5, probably, oh my gosh. This is humbling. Probably like 20 hours.
Okay, so if you're in 17 units, if we scale up 12 as being full-time, 17 units would be a 57-hour work week. So if you're in class for 20 hours a week, you should be studying 37 hours outside of class to hit your full-time status. Your double time status. Like 17 units is not quite double, but it's like time and a half.
Yeah.
It's a lot. 15 is like time and a quarter. So you should plan on like 3.3 hours per unit. So if you're in 15 units, wait, I did my math wrong, sorry. So you should be planning on a 50-hour work week. Just for classes, not anything else. Like in class, so you can take the number of hours you're in class, which is probably a little less than 20. But you can take your number of hours in class, subtract that off, and that's the number of hours you should find for studying outside of class. And it's probably more hours than you think. So when my student was like, I study like 2 hours a week, and I was like, do you mean a day? And they're like, no. And I was like,
how did they even get the homework done in 2 hours?
well, so there was a reason I was meeting with that student separately. It's not going great. So they are increasing their study time dramatically because they don't want to do how they did on the first exam again. Because it's that kind of wake-up call.
I have a question. So like earlier you were talking about reading just like the section summaries.
In the study video.
Yeah. So I know you only like assign certain sections. Do you think it's important for us to like look at the summaries at least for like all the sections in that chapter? Or
Not
just
always.
one?
So like for example, chapter 10, like chapter 3, yes, because we eventually did all of those sections.
Okay.
Chapter 2, yes, because we eventually do all of those sections. There's still a section in chapter 2 we haven't done yet that we're going to do like next week.
Yeah.
Same thing with chapter 4. I think we've done 2 of the sections. By the end of the quarter, we'll do all of the sections.
Yeah.
Chapter 10, we've already done 10.6. This week we're doing 10.1, 10.2. 10.3, 4, and 5 are next quarter.
Okay.
So long term, yes, because if you're taking the full year of chemistry, you're going to do almost everything in the book eventually. This quarter in particular, less so, because we don't do all the sections this quarter.
Okay, I was just wondering if you think it like helps for studying, at least like giving a background on like stuff, or do you think it's just like we only do what we do?
I think, and it's kind of I would focus on the things that we do.
Okay.
Is there value in it? Yes, right?
Yeah.
Like you get to see like the nice thing is you're like, whoa, that's where this is leading. This is what this is going to. This applies to so many things. The thing that becomes problematic is then you might cost benefit analysis. There's a little bit of value in it right now, but if you spend too much time on it, it's more time than the value you're getting out of it.
Okay. Yeah.
So if you're just like glancing through the summaries and being, well, that's neat, totally fine. But if you're like putting time into studying those summaries and trying to understand them, the benefit versus the time cost is just not there.
Okay. Okay. Got it.
I'm gonna go ahead. It seems like people are done with questions. Are there other questions?
I was just gonna ask questions about the midterm.
Sure. I'm gonna go ahead and stop this video and post it.